I'm going to talk about how to generate chirp signals using only addition. Why? Well, we're interested in ultrasound image formation that's accurate. And to do that, it requires using wideband signals. But we also want to do this using low-cost hardware. And chirp signals are wideband signals that can be generated with low-cost hardware. Now, as a side note, the name chirp is a reference to the chirping sound made by birds. And this particular sound starts at a low frequency and it smoothly transitions to a high frequency. I'm going to show how to generate this waveform using just addition. So before generating the chirp waveform, let's look at how we can use this method to generate a simpler waveform, the sine wave. And the way we do this is we simply plot the height as we add an angle to our position going around a circle. So what we do is we just add an angle. In this case, we're adding pi over 16 radians or 11.25 degrees to our position each time step. And we simply plot the vertical height over on the right hand side. So in this case, when we're up here, we're at a maximum height. And then as we keep adding the 11.25 degrees, we get down to here at a minimum height, which we see right over here. And we simply just keep traversing the circle using a fixed angle, fixed pi over 16 angle, and we can generate a fixed frequency sine wave that would go on forever as long as we keep adding that fixed angle. Now, how do we generate a higher frequency sine wave? Well, we just add a larger angle. So in this case, we're going to add a 90 degree, a pi over 2 radian angle, and you can see that we're taking much larger steps as we walk around the circle. And again, same thing, we add 90 degrees, we plot the height here, and then we can get we trace out a sine wave. So one of the takeaways is that the larger the angle that we add each step, the higher the frequency. And if we compare these two, so we look over time, for generating that low frequency sine wave, we added a small angle, this pi over 16, and we just added that angle over time. And here, this is the vertical axis is our angle increment, while the x-axis is our time. And so if we add a fixed pi over 16 angle each increment in time, we're going to generate a constant frequency, a low frequency sine wave. Now, if we want to generate the higher frequency sine wave, as we previously saw, we add a larger angle each time. So we add this higher frequency, or this larger angle each time, and we generate a higher frequency sine wave. Now, our chirp wants to go from a low frequency to a high frequency. So instead of adding a constant angle each increment in time, what we're going to end up doing is varying that angular increment. So for the chirp, we add a changing angle in time. So at the low frequency, we add a small angle, and as we increase the frequency of the chirp, we add a larger and larger angle. And the nice result of this method is that not only do we increase the frequency, but we also are continuous in our waveform, that we don't have any jumps or discontinuities. And so if we see this method in practice, so putting everything together, we see from our previous plot, we start by adding a small angle, which corresponds to a low frequency, and then we increase the step size of our addition until we get up to a large angle, which would correspond to that high frequency. And we can see this on the circle here. As we increase our step size, this angle that we're adding, our positions changing making a larger and larger jump. And what do? We then just plot the vertical height over on the right-hand side, and that vertical height becomes our chirp. So we simply, if we see, we start from our small angle, and then, which is our low frequency, steadily, linearly increase the step size of that angle, and keep adding a larger and larger angle until we get to the high frequency. Now, to see how to implement this in code, let's return back to our Jupyter notebook.